So good, welcome everyone to today's installment of our seminar series, which is also the last installment, at least for now. And today we're discussing challenges in quantifying and assessing information from structural health monitoring. So we go a little bit deeper and look into the fact that we produce large amounts of data, but as we all know, it's not always straightforward to extract useful information from this data, and also the uncertainty associated with this data, how to quantify that properly, and how to combine it with physics-based models. All these will be topics discussed today. We have two of the world's leading experts on this topic here, Geert Lombaert and Costas Papadimitriou, who will, as always, have each half an hour roughly to give a presentation, and we then have approximately half an hour for discussion. As always, you can put your questions and comments in the Q&A, and we will pick them up in the discussion section following the talks. So the first speaker will be Geert Lombaert. He's from KU Leuven in Belgium. He also did his PhD there. And if you look at him, you would not think that he did his PhD 20 years ago. So he is still there, but he did have a few visits and exchanges in other places well known in our field, I guess, École Centrale, UC San Diego. And his research interests encompass a quite broad range of topics that are related to what we do here, including vibrations on structures, inverse problems in mechanics, Bayesian inference, and uncertainty quantification, model updating, of course, structural health monitoring, and multiple other interests. He is very well known. He has given a large number of invited and keynote lectures. I have seen some of those, and that I know that he's a great speaker, and I'm just looking forward to what you're telling us today.
Okay, well, thank you very much, Daniel, for the kind introduction, and many thanks to you and Eleni for inviting me to give this lecture. Let me try to share the screen. Put it in full mode.
Yeah.
Okay, so I hope that's clear. So indeed, I'll speak about the challenges in quantifying and assessing information from structural health monitoring. I'll do that by focus on one particular way of doing this, and that is by state input and parameter estimation. And the work that I'll present is joint work together with Christoph Maas, which is also the result of many other collaborations in the past as well as at present. So those contributions are also acknowledged here. And to start off with the presentation, I'd like to show a number of photos from structures that we are currently monitoring. And these are all structures that we're monitoring within the frame of consulting projects. So one of the things that we'll discuss today is also on how we can transfer the know-how that we have in monitoring to industry, to asset managers. So these are examples of structures where we are currently monitoring. So on the left-hand side, this is a historical railway bridge, a tunnel. This is the a sluice or a lock gate that we're monitoring, and these are some archaeological remains. Now, in all these cases, what we're basically monitoring is, or what the monitoring consists of, is the gathering of data and some post-processing on the data. And so the question that I'll address in this talk is how, as Daniel already referred to, is how we can use physics-based model to extract more information from the data we are gathering. So this is where the input, state, and parameter estimation step in. This slide gives you the mathematical framework, since I'm not sure to what extent all of you are familiar with state space models and filtering. So let me very briefly explain what this mathematical framework consists of. So what you have here in the first equation is a state equation, which dictates evolution in discrete time. So X is a state, and this state would typically contain all the nodal displacements and nodal velocities, or in the case where we work with modally reduced order models, it will contain modal displacements and modal velocities. So this is at the particular time instant, this is at the previous time instant. A and B tell us how we can go from one time step to the next time step. And these can be determined based on an underlying model, which could be a finite element model, as well as a time discretization scheme. So this tells us how the state of the structure evolves in time. The second equation tells us how the data that we're measuring at a particular time step is related to the state of the system as well as the input. So this tells us how what we measure is related to those two quantities. So what we mean by state estimation is that we use this data to estimate the state of the structure. And why would we do that? Well, imagine that you have this railway bridge and we measure strains and accelerations at the number of locations. If those allow us to reconstruct the entire state of the structure, then we can actually recompute or compute or extrapolate our measurements to unmeasured locations. It's an idea that was suggested here in this paper by our second speaker today. So this is the problem which is typically addressed in the Kalman filter, which would give the best estimate under some assumptions for process noise and measurement noise, which are added to these equations to account for unmodeled dynamics, unmodeled input, or measurement noise. So that's the problem of state estimation. Now we can try and go one step further, and in addition to the state, also try to estimate the input to the system, which would here be the loads applied to the structure. Or we can even try to extract more, and that's the final step that we'll take in this presentation, and also try to infer parameters of these structures, parameters which are uncertain, or parameters which may also involve of time. Think of the stiffness of components, which may depend on temperature or other environmental variables. So the idea is in each of these cases to use data and to estimate from these data state, input, or parameters. So basically, these are the three applications. In all three cases, we'll be able to extrapolate response or do what is called virtual sensing. The last two approaches also allow us to estimate forces applied to structures. And the third one also allows us to estimate parameters. What you can see on the left-hand side are a number of different algorithms which are proposed in the literature. The ones which are here given in red or the ones that I'll illustrate in this presentation. But of course, a number of alternatives exist, and I would say that in many cases, the performance of these algorithms is really similar. And I think the challenges that I will try to highlight in this presentation are really shared between these different approaches. So before going to the applications, I'll already put forward the challenges. If you think of, for example, the problem of input estimation, we try to identify forces on a structure based on the response that we measure and a model of the structure. So the idea is to use the structure as a kind of force transducer. And of course, such a force transducer needs to be calibrated. And in a similar way, you can only hope to accurately estimate the forces applied to the structure if you have a calibrated model of that structure. So if you have a very accurate system model, and whatever modeling error you have will result in a biased estimate of the input or of the states or the parameters. And modeling errors that may be acceptable in forward simulations may actually be heavily penalized in the inverse type of estimations that we're trying to do here. So that's one challenge, having accurate system model and dealing with modeling errors, which will always pop up when we deal with real structures. The second challenge is making sure that the data we collect is sufficiently informative. And this is a matter of what is called observability. The example of the railway bridge, which will come back later in this presentation. For now, the thing I would like to stress is simply that we want to reconstruct the state, estimate inputs, estimate parameters. We need to make sure that that information is available in the data that we are collecting, that we have a sufficient number of accelerometers, strain gauges, displacements, transducers, and so on. So that is very important. And another note to make here is that you can derive conditions for theoretical observability, but these are a necessary but not a sufficient condition for successful estimation. There's also something which is called practical observability. Even when theoretical observability is satisfied, the estimation uncertainty may be so large or may be excessive so that the estimates are no longer useful. So what I'll do next is illustrate these types of estimation for applications which involve real-world structures. So I'd like to show what we've been able to achieve for these real-world structures. We'll go from state estimation to input state estimation to joint input state parameter estimation. And you will notice that we go from a less controlled to more controlled environment with a laboratory validation experiment in the last case. So I'll go through these. I'll perhaps remain a bit superficial on the first two and a bit more in detail on the third one. And then the final one is the railway bridge that you've already seen in the previous slides that I'll also use to highlight some challenges. So the first application involves an offshore monopile wind turbine where we've used data which was kindly provided to us by the colleagues from VUB in Brussels and OE Lab. And the data here consists of accelerometers and strain sensors, which have been applied to, let's say, a number of positions at different heights of the wind turbine tower. So those are the data that are available. We've created here a system model. I won't give any more details, but I'll indicate here that the mode shapes and the natural frequencies are those from an updated finite element model. So it's a modally reduced order model. So with mode shapes and natural frequencies of the updated model, and those combined with the experimental model damping ratios, so that we have indeed a model that is as accurate as possible. Now, this entire data set has been subdivided into a set which has been used for estimation. These are the quantities which are indicated as measured here. So the A indicates the accelerations, and here you can see these strains. And we'll use this data from 3 different heights to estimate these strains at the lowest level of the wind turbine tower. This is done by a Kalman filter. Very, very briefly, what you have is some initial estimate of the state. You see how that initial estimate links up with the data. Based on this discrepancy, you correct the initial estimate to arrive at a final estimate. And so this combination is done in a way that takes into account measurement as well as process uncertainty. And then once this estimate has been made, it's moved forward in time and the process is repeated. So this gives you an impression of the results. So what you can see here is strain in 2 different directions, fore after and side. So this is at the lowest level of the wind turbine tower, which was instrumented, a full time record, and then a detail of the time history, as well as a representation in frequency domain of these strains. And what you can see here is that the measured and the estimated strains agree quite well. They correspond very well, I would say. So indicating or suggesting at least that here these techniques can indeed be usefully applied for this kind of virtual sensing or response extrapolation. Next comes an example where we consider, in addition to the state estimation, input estimation. This is also a case which involves an offshore wind turbine, although here it will be a scale model which was tested in a water basin. And here we've applied the algorithms to estimate breaking waves which are generated in this water basin. And this is very useful because these breaking waves are not easy to predict. And so having in situ measurements and using the structure itself as a kind of force transducer can provide very important design feedback. And so this is also one of the opportunities for these algorithms. So, well, the bottom figures give you an impression of the wave pattern. So it has quite long length and width and height. There are wave generators, which can be used to generate the waves and also focus the waves such that they break in front of the wind turbine. We have the scale model of the flexible monopile, and then we have a rigid substructure next to this to collect information on the incoming wave field. Basically, our reference for the input estimation or the force identification is coming from this second structure. Here as well, here in this case, we've simply built the system model based on experimentally identified model characteristics only. So in this case, it's again a modally reduced order model, but only with experimental characteristics. Here you can see a number of accelerometers over the flexible tower. We've used data from accelerometer 2, and then here you can see the pressure cells which were used to verify the solution of the input estimation. So here in this case, in addition to the state, we also estimate the input. So we compare the initial estimate of the state with the data to estimate the input, and then with initial estimate and the input and the data, we also update the state. So again, what you can see is a full-time records of the horizontal wave load as well as the overturning moment, and comparison of the measured and the estimated quantity. So full-time record, more detailed time history, and then a frequency spectrum of the force. So here again, the agreement is quite reasonable, but of course, one of the things that stands out if you look at these results is the spurious oscillation, which we can see in the estimated input, in the estimated force. And these also appear as a peak here in the spectrum. And these actually originate probably from modeling errors, which have quite a large, which have a large influence at the anti-resonance frequency of the structure. So that's what the peak is associated with. And then going one step further, you can notice that we come to a more controlled environment in this case. So in addition to the state and the input, we now try to estimate a parameter. And for this, we've set up a test in the laboratory. So it's a steel beam suspended to flexible springs. And then on this steel beam, we actually fixed a number of magnets with a mass which corresponds to approximately 1% of the total mass of the steel beam. And our intention was to use the parameter estimation to estimate the mass which was attached here to the beam. So we assume the location of the mass to be known, and we try to estimate its magnitude. So we've used an instrumented impact hammer and also a number of accelerometer and strain gauges distributed over the structure. So again, here the model is a combination of things which have been updated or which are based on an updated or a calibrated finite element model and experimental model quantities. I won't go into a lot of detail, but one of the things that we've looked at in our research was the use of smoothing algorithms, which differ from the so-called filtering algorithms which were presented earlier, in a way that also future measurements are considered in both the input estimation and the state estimation. And this helps to smoothen out or to cancel out some of the estimation errors which appear in the filtering. So that's one thing I like to point out. In addition here, I'd like to indicate that the state here is an augmented state, which does not only contain the actual state of the structure, but also the parameter, which in this case is the additional mass attached to the structure. What I'll compare here are results for two sensor configurations to highlight again the importance of having an appropriately designed sensor network for this estimation. So the first set contains all accelerometers as well as two strain gauges, and very important is that this contains a collocated measurement. And collocated means that the acceleration is taken at the point where also the input is applied. And this is extremely beneficial for the input estimation, as you'll see next. So this is the main difference with the second set, which contains less accelerations, but the most important thing is the collocated measurement, which is not included here. So I'll compare results for these two sets, as well as for two different delays where, well, a delay of 0 corresponds to the filtering discussed or considered earlier, and then a delay of 5 means that we consider in addition 5 future data points for the estimation of the input and the state. So this is a result for sensor configuration S1. Again, full time history, detail of the time history, and these two figures here are for the input, the actual force, and you have 3 results which are basically on top of each other. So the errors here are quite small. So you can see how both the filtering and the smoothing give an estimate of the force, which is close to the true value. And then the third figure here shows the mass which has been estimated from the experiment. What you can see is that until we apply the impact, we stay with the initial value. And then as soon as the impact is applied, you can see how it sort of gets closer to the actual value. It's not perfectly on top. And this, as well as the variation which can be seen in this mass, is due to modeling errors. This is for the second set of sensors, a similar result. So the most important difference is the lack of a collocated acceleration measurement. And you can clearly see how this has a large impact on the estimate for the filtering algorithm. You can see basically how the impact is now estimated as a force which has a very oscillatory behavior as opposed to the original impact. When it comes to the estimate of the parameter, that seems to be less sensitive to these additional inputs which have been taken into account, or the additional data points which have been taken into account in the smoothing. So these results indicate that there is at least some potential in these methods. I think if I take together all 3 examples, it indicates that we can expect these estimation methods to actually work in the field on true structures and are very useful for integration in a monitoring system. What I'll focus on in the remaining part of the presentation is a study that is still ongoing, where we apply this method for on a steel bridge, a steel railway bridge, which is close to Leuven, which we've been monitoring for 2.5 years. The focus will be on the monitoring of strains for fatigue consumption, in line with the original idea that was already explained before. In addition to this, it's a kind of byproduct, and I won't go into more detail in this presentation, but we also have natural frequencies and mode shapes of this bridge in damaged and repaired conditions. So as we were monitoring the bridge, we noticed some damage at the connections between the diagonals and the arches. This damage was repaired, and so we have natural frequencies and mode shapes in the original condition, in the repaired condition, as well as during the ongoing of the works, which also includes some influence of the scaffolding. But I'll leave that for now. If you're interested, please get in touch. So I'll focus on the strain sensing. So again, the idea is the same. We collect data from the structure on the one hand, and we combine that with a physics-based model, which is the detailed finite element model shown here. And from this, we try to do virtual sensing and extrapolate to unmeasured locations. Yeah, so this detailed model was again calibrated. So we did a quite extensive operational model analysis on the structure, and then based on this operational model analysis, we've calibrated the finite element model. We've adjusted the ballast stiffness. We've also adjusted the stiffness at the supports, which was basically telling us that these supports were fixed, at least for this type of excitation. And so this helped us to obtain an accurate finite element model. This gives you an idea of the instrumentation layout of these structures. So we have a number of accelerometers on the arches of this bridge, on the bridge deck. We have quite a large number of strain gauges on the main girders, as well as on some of the diagonals. We also have displacement transducers at the bearings. I'll come back to these at a later stage. And we also have strain gauges on the rails, which are about here. I can't see it because some of the zoom windows are in top, but these strain gauges on the rails basically allow us to identify axles, identify the number of axles, the distance between the axles, and also the speed of the train. So it allows us to reconstruct the axle positions for a train that crosses the bridge. In addition to this, we measure temperature, relative humidity, so that we can somehow correlate all these quantities to the environmental characteristics, and also fiber optic sensors on the main girders have been added recently. While we were measuring the response of the bridge, we noticed that the bridge was behaving very stiff, and so in essence responds in a quasi-static way to the train. So we've simplified the state equation in a sense that we got rid of the damping and mass matrix in the finite element model, and we here have a relation between state, or no, not a state, but simply the bridge displacement, and the loads, which is given by the stiffness matrix, and this matrix which contains the information on the positions of the axles. So when we have a time-dependent response of the bridge, that time dependence is only governed by the fact that the positions of the axles change with time as the train crosses the bridge. We assume these positions to be known, and the only thing we estimate are the magnitudes of the axle loads. So that's what is contained in the vector P, and those are estimated from a subset of these trains which were measured on the bridge. This gives us, or this gave us, this first initial result. What you can see in the top row of figures is the strains which were used as input to estimate these axle loads. And what you can see is that the measured and the estimated strains agree quite well, which makes sense because the loads have been determined by least squares fit of these. And then what you can see on the second row are the validation data. So these are strains that we predict and then compare with the actual measured strains. And you can see that here the agreement is, it's not very bad, but you can see some discrepancies in those estimations. Now, this puzzled us for some time, and then what we finally noticed was that the boundary conditions, which we assumed to be perfect roller supports here, were not behaving as we expected. And so this, or these figures here to illustrate that behavior, so we installed a number of, or we installed 2 displacement transducers. And what you can see here is what we measured and estimated during a train passage. So you can see the longitudinal displacements at the bearings, and you can very clearly see how the measured displacements do not return to 0 after the train leaves the bridge. And this is basically because of nonlinear behavior of the bearings and friction preventing the bridge from returning to its original position. So that's something we then took into account in the estimation, and basically what we did was make use of a linear superposition to write the response of this bridge as one which is a combination of displacements imposed at these supports. And here we use the information on the measured displacement, so those are used as input in this estimation process as well. And then the actual train loads on the structure. So we have a slightly modified equation here, which also takes into account here, these two should be identical, the displacements at the supports. Now, one of the things which is still bothering us is that this relation between the support displacements and these strains, we were not able to accurately reproduce this relation from the model. So this is up to now something where we've actually used our data, our measured data, to relate displacements, eddy supports to strains at all measured locations. So it's something that we're still working on, but I think it's something that will be encountered for many structures at some point. I think you hit a limit of things you can predict, and I think at some point always, I mean, as you try to go more and more accurate, there comes a need for data augmentation and correction for your model predictions. So this is something which I think is very relevant. I think the idea we have applied here, and this is also the reason for the reference at the bottom of the slide, is a very simplified way of general structure framework, which was recently presented. So that I think will also prove very useful in future. So with this improvement of the estimation, we come now to better results. So again, these are the results which have been used for the virtual sensing. And now you can see how we have a much better agreement for the validation data, but then also using this measured relation for, between displacements and strains, as this was not accurately reproduced by the model. So with this, well, I'm ready to conclude. So with these examples, I hope I've convinced you, or I've demonstrated the potential of these kinds of estimation algorithms for the various types of estimations, response or virtual sensing, force identification, parameter estimation. I think it provides very useful information to verify the actual performance of structure, and in this way also providing important feedback for the design of new structures. And then, as highlighted in the presentation, one of the challenges is to have a very or sufficiently accurate system model, where possibly you'll need to use other techniques to correct the model, as well as having a properly designed sensor network, which is sufficiently informative. So with this, I'll conclude. I'm happy to take any questions, unless, Daniel, these questions will go into the discussion that we'll have at the end of the two presentations.
Yes, maybe I can reply. This is the case. So we will now introduce the second speaker, and then we will do a roundtable sort of discussion in the end. But since you mentioned this, it's good to invite the audience to already maybe pose some of their questions in the Q&A, because we will bring these up. So we will draw from these questions also later on in the roundtable. With this, maybe I can then take the floor. I want to thank you, Geert, for a very nice presentation, always educational for me at least. And I would like to then introduce our tandem speaker. So the second speaker for today, this is Professor Costas Papadimitriou, who has, maybe to give a bit of information, has received his master's and PhD degree in applied mechanics from Caltech. Later joined the University of Thessaly in Greece as an associate professor of structural dynamics, and is now a professor at the same institution. He has had a number of different awards as part of his career, including the European Association of Structural Dynamics Senior Award. And I'm not going to go into the long list of honors. I just want to say that I have known Costas for a long time, almost my complete academic career. And I'm very fortunate to have him as a collaborator, really offering inspiration and almost pioneering ideas in the field of Bayesian methods. And I think he will be discussing a bit of this in what comes next. So the floor is yours.
Thanks, Eleni. I'm trying to share everything probably. Yeah, that's.
It's not yet full screen if you want to try. Yeah, now it is.
Okay. So thanks for the very good words that you came up with. The title is similar here, and I'm going to present two issues here. How to quantify properly the uncertainty from multiple data, and I'm going to use a hierarchical Bayesian modeling framework, trying to persuade you that this is the right way. And the second issue is what data to collect, and I'm going to talk about Bayesian optimal experimental design. Actually, what I'm going to assume is that I have a physics-based model, say a finite model of a structure, and I have model parameters that I need to infer, and I'm going to use Bayesian inference to learn about these parameters. And I have to recognize that whatever model you have, it does not perfectly describe the real dynamical system. And we call this model error. And due to model error, if you have two different data sets and try to identify the model parameters, you'll find out that you'll get different estimates. So the identified model parameters demonstrate predominant variability when identified from different experiments. And here I will assume that there is no environmental variability, there is no operational variability, okay? Just the model error, the fact that my model is not representative of my system. This inherent variability is irreducible, even if new observations are used. The uncertainty that we estimate when we use the classical Bayesian approach does not account for this variability. Okay? And we know that as you get more and more data, the uncertainty from classical Bayesian approach reduces, all right? And goes to zero, you have a lot of data. So you end up with very small uncertainty of that. So in the presence of these modeling errors, these Bayesian methods seldom give a realistic account of uncertainties. We're going to bridge this significant gap by introducing the hierarchical Bayesian modeling framework. What is this? What we try to do, if we have some model parameters, say theta here, okay? We embed the uncertainties into the model parameters by assigning a distribution for the model parameters, say a Gaussian distribution, with say the mean and the covariance of that Gaussian distribution to be hyperparameters to be estimated from multiple data sets. So the data set, one data set of all these data sets, say here, we have multiple data sets DI, and the data set DI is used to infer an independent realization theta I from of the model parameters. One, in order to set it up, goes through this regular Bayesian framework with a prediction error for each data set. You can have any probability model for the prediction error. And then he can eventually develop through the hierarchical Bayesian modeling framework the posterior distribution, not only for all these theta i's which correspond to different data sets, as well as the prediction error variables, I call them here sigma I, but also jointly, we have here the hyperparameters, which is the mean and the covariance matrix of the Gaussian distribution assigned for the model parameters. The idea here is to estimate the posterior probability distribution of the hyperparameters. Then everything is easier and you can propagate all the uncertainties. We have done all this using as data sets input output time histories and as parameter structure related parameters. We have also done it using as data sets output only time histories as parameters to be estimated the modal properties. We have also done this using as data sets modal properties identified from multiple data response time histories and parameters to be structural properties. Some details change in the formulation, the hierarchical Bayesian formulation, and the details also depend on what you assume for the prediction error, how to infer it. Okay? And the framework, in the framework, you actually develop the likelihood of all the data. And when you try to develop the likelihood of all the data, what is involved is the likelihood of a particular data set given the parameter values theta I. And the only thing that we do different from, we try to do different and not use sampling approaches, is to approximate this likelihood for each data set by a normal distribution. Okay? Normal distribution that is has mean the most probable value of the likelihood at covariance, which is the inverse of the Hessian of the minus log of this likelihood. You could do this. It's an approximation, which turns out to be extremely good. It holds for a large number of data within a data set. And then you can develop the marginal posterior distribution for hyperparameters, the mu theta and sigma theta theta. That's what you need. You get develop a nice analytical formula for that. And this formula gives you valuable insight on this hierarchical Bayesian formulation. For example, you can go ahead and under some conditions, you can find out that the most probable value of the hypermean, okay, is the ensemble mean that you would get from the parameter estimates, optimal parameter estimates for each data set, while the hypercovariance depends on not only on the ensemble covariance, but also on what we call the identification precision, which has to do with the uncertainty that you get when you estimate the model parameters for one data set, for each data set. Of course, you can also go ahead with this and compute the uncertainty in the hyperparameters, and you can show, this is a lot of mathematical details, that this uncertainty reduces as you increase the number of data sets. The uncertainty in the hyperparameters, mu theta and sigma theta theta. And of course, you can use sampling to propagate uncertainty in the parameters through your system and compute uncertainties in various response quantities of interest. What we have accomplished is to embed uncertainties into the model parameters and be able to propagate uncertainties. In the Bayesian, usual Bayesian framework, part of the uncertainty is embedded in the prediction error. And when you estimate the prediction error for the accelerations, if you measure accelerations, you have no idea what is the prediction error for the displacements, strains, and so on. So this is powerful in terms of embedding all the uncertainty or whatever uncertainty you can in the model parameters, because you get realistic uncertainties in the predictions, as I will demonstrate. Also, one point I have to make is that here you have to solve independently as many problems as the number of the data sets. So you can use parallel processing to do that, all of that in parallel. And to sample from this distribution, because you have to sample in order to propagate the uncertainties in the hyperparameters as well, you don't need to run any model. The model runs are involved here. Okay, I will demonstrate with an example here. This is a numerical example where I use a nonlinear model with bilinear nonlinearity as my system, and I use a linear model as my model that I try to update. So data comes from the nonlinear model. The model is linear, so I have a model error. And I generate from the nonlinear model 100 data sets. Okay? And my input is white noise, but to generate the 100 data sets, I use the same strength of the white noise. So operational conditions, the same. The excitation characteristics are the same. The details in the white noise change. So I use these 100 data sets to estimate parameters, say the stiffness of my linear model. Here you can see that the blue dots that you see here, I plot stiffness versus number of data sets, and the blue dots are the values of the uncertainties and the identification uncertainty that you can hardly see. These are means plus 3 standard deviations for the blue dots that you see here. For each data set, when I process each data set. So the identification uncertainty is extremely small, while the color area that you see here show the uncertainty bounds that are produced from the hierarchical Bayesian modeling framework. And these uncertainty bounds are identified for the stiffness. And you see large uncertainty bounds related to the identification uncertainty for this example. And you can also see that as we increase the data sets, these uncertainty bounds stabilize. Okay, so actually we get uncertainty which is large as an irreducible. Here you get propagation of uncertainty from non-hierarchical and hierarchical method. From the hierarchical method, the uncertainty, okay, contains the experimental data, while from the non-hierarchical method, the uncertainty that is propagated from the model parameters does not contain the experimental data. We have done all this work also for a 3-story prototype structure. This is a real experiment. The input is Gaussian white noise at the base. The measurements are the acceleration responses at the 3 floors. We have generated 20 data sets using, though, the same intensity in the excitation when we excite it with white noise. Okay, our model is a shear building, 3 degree of freedom shear model of a building. Say, okay, we have 3 stiffness parameters and 3 damping ratios. Okay. And here is just a reasonable accuracy that we get in predicting the acceleration response time history from a data set. Okay. And here are the uncertainties of the model parameters that we predict from the non-hierarchical Bayesian approach. And you can find here that the standard deviations of the parameters are extremely small, which means that the uncertainties are extremely small as compared to the standard deviations of the model parameters that are inferred from the hierarchical Bayesian approach. The mean values are almost the same for both approaches. This means that the non-hierarchical approach provides unreasonably small uncertainties, as expected. The hierarchical approach gives more realistic account of uncertainty. And of course, these findings show the great potential of the hierarchical Bayesian framework to enhance the robustness dramatically. These are the plots again of the uncertainty versus the number of data sets, similar plots that I showed for the numerical example. Okay, I will not stay into that. And these are the predictions that I make from the non-hierarchical method using uncertainty the model parameters. And these are the predictions from the hierarchical method where the uncertainty bounds contain the experimental data. Right. We have done all this, we have repeated this with modal properties instead of time histories. Now the parameters are only the stiffnesses, the 3 stiffnesses. And here is the case where the data, the number of data is small. We have 9 data, modal frequencies and mod shapes for this structure. However, we compare the asymptotic approximation, the values of the hyperparameters, with the full sampling, and we get very good results, even for this small number of data. Of course, if you compare this with the classical Bayesian framework, the uncertainty values are extremely small compared to what you get with the hierarchical one. Then we took the uncertainties in both parameters, stiffness parameter values and the prediction error uncertainties, and we propagate them to the modal properties. Here you see the propagation to the modal frequencies, which are normalized over the nominal values. You see that the hierarchical Bayesian framework and the conventional Bayesian framework give different kind of uncertainties. Here you get a strong correlations, here you don't get a strong correlations. The uncertainty level is the same. Now we try to propagate uncertainty to find the posterior distribution of the maximum interstory drift, completely different results in the left figure, or to the exceedance probability given a drift level, and you get orders of magnitude differences in those predictions, okay, from the two frameworks. We have repeated this work for the case where this is a pedestrian bridge, ambient vibration tests or output-only vibrations. Our goal here is to estimate modal properties. We use 6 sensor locations of the bridge deck. We have taken here 19 data sets. Each data set corresponds to 5-minute response time histories. Okay, and we try to build on approaches like the Bayesian FFT approach developed by these guys. Ivan Au has done a lot of work on this. And we try to develop on this our hierarchical Bayesian framework. Okay. I want to remind you that this Bayesian FFT approach gives you uncertainty in the model parameters, but gives you the identification uncertainty, gives you the identification precision. It doesn't give you the uncertainty due to the variability from different data sets. We got the uncertainty due to this variability. I'm not going to show a lot of results. I'm going to conclude here with each mode. What is the uncertainty? You find here for the first, second, third, and fourth mode. It turns out the uncertainty, the modal frequencies is of the order of 1%. The uncertainty in the mode shape components is of the order of 5% approximately, while the uncertainty in the damping ratios is much larger, extremely large. And this is the uncertainty due to variability from the different data sets and not the identification uncertainty. So I'm going to skip all this. When you use these Bayesian computational tools and you have large models, you run into problems, computational problems. You can use surrogate techniques. I just give you this slide to see that you can use different surrogate techniques or model reduction techniques, physics-based model reduction techniques. You can find details in these formulas to reduce substantially the computational effort if this is needed. Concluding remarks is that the classical Bayesian learning framework severely underestimates uncertainties. The hierarchical framework, built on existing Bayesian formulations, promotes the idea of embedding uncertainties into system model parameters, captures the variability promoted due to modeling errors, accounts for both identification precision and ensemble variability, promises more realistic quantification of uncertainties. I have given you some examples. Incorporates uncertainties that are irreducible, leads to robust propagation of uncertainties, predict output quantities of interest with a reasonable accuracy, producing reasonable uncertainty bounds, and of course deploys existing efficient computational algorithms. This is a reference list. You can glance through important authors here, Mulvaney, Lombard, the first speaker. This is a PhD student, is a postdoc student in Hong Kong, my student here. And a lot of ideas were transferred from Koumoutsakos group at ETH. This is similar frameworks, hierarchical Bayesian frameworks developed from molecular dynamics from Koumoutsakos group. I'm moving now to Bayesian optimal experimental design. What is that? Help us to select the best experimental setup out of many alternatives. What is best? The best is the one that yields most informative measurements for the purpose that we want, either to select models or to infer model parameters or to virtual sense or reconstruct responses like strains. Design variables are usually the type, location, and number of sensors if we don't know the inputs, but if we can excite the structure, it could be also actuator locations and excitation characteristics. To do all this, we need to build a measure that quantifies the information we gain from an experimental setup. I'm not going to go into the details, but such a measure is the KL divergence, which gives you actually the distance between posterior and prior distribution in a Bayesian setting. Okay? And if this posterior and prior are the same, it's actually you don't gain anything from the data. Okay, if they differ, the more they differ, the more that you gain from the data. So you try to maximize this scale divergence. This scale divergence depends on the data that you don't have. So you generate the data from the prediction error model that you set up to the Bayesian formulation. So you actually maximize the expected scale divergence over all possible data that you can generate. And delta are the sensor locations. Phi are nuisance parameters, parameters that you don't want to infer, but they are uncertainties can impact designs. Okay, and of course, if you want to define a robust measure, you integrate also over the possible values of these nuisance parameters. Right? And we have done a lot of work here. The first speaker has contributed a lot. Here is the type of analysis that you could do, optimize for parameter estimation, response prediction, damage identification. The models that you could use are linear, nonlinear models, could be known input, unknown input. And I'm going to say here a few words about the methods that you use to estimate the integrals that I presented. Methods could be sampling methods that you don't learn anything out of this, you just use them, or asymptotic methods that you can learn a lot out of this. Okay, for example, for parameter estimation problems, you can learn that the place where you place the sensors to locations where the response is most sensitive to parameter changes, and these sensitivity measures are hidden here in the Fisher information matrix, and it's the log of the determinant that it counts, and not the determinant. For other reasons, I don't have time to explain. When you want to choose the excitation characteristics, you choose the ones that provide the responses that are most sensitive to parameter changes at the measure locations, of course. Okay. We have talked about using the structure of this nice asymptotic approximation. We have talked about that using correlated prediction errors, we can avoid sensor clustering and redundant information in a paper by the first speaker. And also you can go ahead and show that the information that you gain decreases as the model and measurement error increases. I'm not going to present results from this, but I'm going to stay in these results. I'm going to assume that I want to design sensor location to predict responses. Okay, so I'm going to design, I'm going to use sensors to estimate responses so that, and my question is, where should I place them so that I can predict responses at all other locations? And my input is unknown. and my model is linear, it turns out that if your posterior PDF of your responses that you want to predict follows a normal distribution with covariance matrix, which is independent of the data, you get a nice formula for the information entropy hidden here. Okay. And this actually formula does hold when you have a special case of linear system and you predict, you make predictions using modal expansion. This formula that you see here is covariance matrix is given by this formula. I will not stay into the details on this. Or you could do the same. You get the exact formula for the exact expressions. When you use joint input state estimation techniques, you take the steady state response for that. And this is a selected list of filtering techniques. And in the results that I will show you, I'm using the augmented Kalman filter. In the results I will show you, I'm assuming that I have strain sensors that I have to place them in a plate that is fixed at the left end, free at the other ends. I have a finite element model for the plate which has 440 finite elements. Prediction, I would like to place sensors, a few sensors, so that I want to predict strains everywhere at the 440 finite elements. Okay, along the x direction, the horizontal direction. And I'm going to assume that only 8 modes contribute. This is important, how many modes contribute. And you can see here results which tell you what is the information that you gain. This is the normalized information that you gain versus the number of sensors placed at the optimal locations, the top 3 curves. And this information gain is normalized by the information that you gain if you place 440 strains all over the structure. Okay, so it turns out that if your measurement error is extremely small, okay, 8 sensors can do the job. Why 8 sensors? Because for the modal expansion, this is the modal expansion method, you do need 8 sensors to get a system which is identifiable. With fewer than 8 sensors, you don't get identifiable. You borrow information from the prior. This is not good. Okay? If you have a large measurement error, where you place your sensor, you have large measurement error of the order of 5%, I think it is in this case. Okay, with 8 sensors, you don't get 100%, almost 100% of the information. You get 80%. And as you need to add more and more sensors to get information. And here is a case when we did a robust design where we assume that we don't know the measurement error is between the green and the blue. Is 5% to extremely small, and we get as information gain this line here. If you look at the optimal sensor placement, you'll find out that for extremely small measurement error, you place sensors at these 2 ends. Sorry. The strains here are extremely small. However, if the measurement is very, very small, then the noise to signal ratio is extremely small, and these are valid locations. As you increase the number of, you increase the measurement error, you move away from here towards the left. You place sensors toward the left, you don't place sensors here. And of course, for large measurement error, you place sensors at the green locations. When you use a robust design, you tend to place the sensors close to the green locations. These are the predictions that you make using the modal expansion. Here we run with an input white noise at the location. We made predictions, and then we use 8 sensors at the optimal locations to predict at all other locations the strains, and we compare the errors between simulated data and the prediction that we made with 8 sensors, and we find out that for when you place the sensor at the optimal locations, the errors are of the order of 1 to 2%, When you place the sensors at arbitrary locations, 8 sensors, the error is higher. And when you place 10 sensors, not 8 sensors, at other arbitrary locations, the error could be much higher, as you see here. Right? These are now the predictions from HAF, the information, the normalized information gained from HAF, right? With respect to the number of sensors. You can see here that you don't need 8 sensors to get the information gained. With 6 sensors, you get most of the information that you would get with 440 sensors. With 4 sensors, you also get, with 3, also you get a lot of information. Something which is completely different from what the modal expansion gives you here. You need 8 sensors to get information. Okay? And if you look at the positions of the sensor from modal expansion and AKF, they are almost the same. It's just that the modal expansion cannot deal with less than 8 sensors, while the HAF can deal with that. And again, here the predictions from HAF, you can see it with 6 sensors, you get very small errors, less than 2%. Same with 4 sensors. With 3 sensors, you get large errors, but this is due to the fact that we use here the approximate methods to optimize, like the sequential sensor placement. And if you use GA, you do improve on this. These are some references. The important guys, you see them in blue. The first speaker, and references on the use of this method in other areas like life sciences. You have them here. I would like to acknowledge my collaborators here. The first speaker, of course, Moaveni, the group from Hong Kong, Dr. Sedehi and Lambros, Petros Koumoutsakos group, and my students are here, and the family. Thank you very much.
Great.
Thank you very much.
Yes.
Yeah, go ahead.
No, thanks to both speakers, and I think we have a lot of very interesting ideas and yeah, input. And I think again I ask everyone to just type their inputs and comments in the Q&A, and we will pick it up. But maybe I will start with something that comparing the 2 presentations and thinking about the one theme that was in both presentations, which is the quantification of uncertainty that we have in our predictions. And I thought that in the first presentation, Geert was showing kind of the frequentistic approach, using validation to basically figure out what is the error that we make, versus kind of the Bayesian approach using your hierarchical model to do that. And I was wondering if in which way we could actually combine the two. Or I mean, this is not really thought through now, but but you did show quite different approaches, and they both have their pros and of course cons. So if you want to do the validation, you need somehow to observe also the quantity that you want to predict in some way, which is not always possible.
Let me say that what Geert has presented is a recursive Bayesian filtering approach. I presented a kind of batch approach. So there are 2 different approaches. Now to how to use a hierarchical Bayesian framework with Bayesian filtering, I don't know. We have tried to think about this. I don't know.
Yeah, but I did not really refer to the filtering. I mean, but I refer to the fact that Geert in his presentation is showing, because validation is kind of or use you make a prediction for quantities that you also observe, but you don't use them, and then you use that for validation. And in my mindset, this is kind of, and then that's what we use in machine learning and so on. Cross validation is frequentistic concept for quantifying your model uncertainty. And of course, the methods that you use them behind it are maybe Bayesian and so on. But because this is for me, this is kind of the holy grail here in many of the things we do. Is like, how do we all the time work with models, and we want to, and then we have also now monitoring, but still we're doing it model based. So how are we able to tell us how good is our model? And I think this is both you try to do that.
Yeah, I think that is a key question, and I think the addressing of model uncertainty is really a challenge. And I think the hierarchical approach is definitely a nice way to incorporate some of the model error and lump that into the parameter uncertainty. I think in addition to that, there is probably also a part that will always be difficult to cover by a physics-based model, and so I think we'll always have to take into account some kind of model discrepancy in some way, where indeed you need to rely on validation for information on that model discrepancy.
There seems to be a question, maybe if in the chat. Let me see, but it's directed to Daniel, so I'm not sure if it is on our topic.
Yes, this seems to be. I will
this is more on Bayesian networks, so we can do
I
it
will
separate.
answer it separately.
But maybe then I can address a question that ties. Okay, so what Geert and Costas showed are actually frameworks that now are, in a sense, quite mature. Even Geert made the case that now we can actually implement these on real structures because of the maturity of the algorithms. My question would be, is there a way that you see is the best practice for connecting these to this concept of value of information through your exchange with, and I know you both have exchange with practitioners and operators. Do you think we need to do this very explicitly? Is it enough to just show them the results of the kind of predictions that you are giving? What would be your opinion on quantifying, let's say, the benefits?
Eleni, I think what I showed, and probably heard, is how you quantify uncertainties. And these uncertainties help you later as you monitor the structure and there is the damage, okay? All these hyperparameters that I show, if you still keep monitoring, they have to change. And these changes can indicate damage. Until you do that, until you really damage the structure, see that this damage is manifested into these parameters, and you really able to demonstrate to these guys, to the practitioners, that you can do this, okay? This is the actual thing that one has to do, all right, to demonstrate that such a technique is valuable. Okay.
But I assume there have been a few attempts, also on these benchmarks on real life structures, and I guess what you mean is that we need more instances of actual implementations that demonstrate this to be convincing, I suppose, right?
Yeah, Hertz have shown some real good applications. Yes. Okay, these are extremely good applications. Okay, on bridges and on the wind turbine.
Yeah, the reason why I included the slide with the 4 structures at the beginning of the presentation was to highlight a bit the difference that there still is between the monitoring projects that we're doing within the frame of consulting and then the research. So in those monitoring projects that we do within the frame of consulting, that's the emphasis on the data gathering and a limited post-processing. And so what we're trying to do now is convince these infrastructure manager also of the value there is in combining these data with models to extract more information. And we see an increased interest, at least, I mean, in our group and the organizations that we work with, but it's it's still, I mean, not at a stage where we're implementing yet. So we see an interest in digital twins, in using and gathering data from sensors and fusing that with structure. But then often the question is what at the end is the gain. So I think this links up well with the value of information that you mentioned, Eleni. So I think apart from showing what we can do, probably they also need some cases where the benefit is demonstrated.
But I think, you know, this kind of fatigue prediction, Eleni, I think we're ready to show these things.
Yeah.
Okay, I have shown this clearly, okay, in the examples. These filtering techniques tend to work. Okay, you need some tuning, but they tend to work. But even if they don't work well, they can guide you as to where the fatigue will occur. Okay, based on what measurements you have collected up to now. They don't have to give you the exact picture, because anyway, fatigue formulas are very approximate.
Right.
You don't expect your response time history to be exact and the fatigue formulas to be very approximate. Okay, there should be a balance there. I think in that direction we have made steps ahead, that we can now are ready to demonstrate to these practitioners that this works not only for bridges, also for other structures like you know, heavy vehicles. They have similar fatigue problems, not only in the vehicle structure but also in the components. Okay, and we can demonstrate all that. There are also studies that have demonstrated this. They used our lead, whatever. Okay, our means everybody who's working over here, and they have demonstrated this.
I would guess that then a necessary next step is to make these tools easy for them to operate, because a lot of the tools, as that's what I understand also from our interactions, might exist at a level where a researcher can use these, especially if they are adept in coding, let's say, but are not so easy for them or interactive or intuitive for practitioners, let's say, to adopt. Is this something you have considered as well?
I mean,
It's
you know,
not. No.
Yeah.
Go ahead, Costas.
No, if you go to a practitioner telling that, you know, I want to instrument your breeds and do whatever this, and this, the first obstacle is who is going to pay to instrument the breeds? This is the first obstacle. Okay, probably Hert is very lucky to, but here in Greece, I'm not lucky. Okay.
Well, the case of the railway bridge there, I mean, that's also within the frame of a research project. So there we had funding for the instrumentation. But the other 4 projects, I mean, there we were actually paid to do the instrumentation and gather the data.
Maria Pina, you can just talk. So you are...
Okay. Yes, I want to make some comments regarding the last questions. I think my impression is that operators are more interested in how to manage the maintenance, for example, how to manage the emergency rather than knowing if there is a damage. And to provide the support to, let's say, how to manage the maintenance, what we really need are models that allow to prognose the evolution of damage. So, and these, I think, are still immature from a research point of view. So they are not really applicable. But this is the direction where we need to go, because when the owner knows that there is a damage, then he has to do something. And sometimes for them, it's a problem because they don't have a protocol. So now I know that there is a damage, and now what shall I do? And sometimes doing something is possibly has possibly a higher consequence than not doing anything. The example that always comes to my mind, imagine a football match, the football match between Italy and someone else in the next days. Someone says that the monitoring system of the stadium has some problem. And then the manager has to decide to close not to allow to play the match. And there is not a protocol. There is not a protocol because maybe the monitoring system just tells you, okay, the threshold has been exceeded. Now it's up to you. You decide if you have to close the stadium or not. This is a problem. And sometimes the manager doesn't want to know, doesn't want the monitoring system, because this is a responsibility. So what we really need to have, first of all, to manage maintenance, we need the prognostic models so that they can use these to decide when to perform the intervention. And then we need protocols that tell the owner, now you have to push the button or not. So I think this is somehow missing more than the scientific development on damage detection.
But isn't it also, and this is my experience with some projects, that when there is a damage, and as you say, that often there is, or typically there is no good model to predict the damage. Even the fatigue models are often not that good. But for other damages, they don't even exist. But then often the monitoring, or by putting some kind of monitoring the damage, and maybe that's just very simple monitoring, because when you know what the damage is, it might be often quite trivial, but monitoring the damage is a way to live with the fact that you don't have a good prediction. So you look at how it evolves in time, and then you see, okay, it's maybe it's not growing exponentially, but it's maybe not growing at all, or it's growing under certain circumstances. And at least in the project, in some projects that I have been partly involved, that was used as a way to kind of make decisions.
Yes, this is what I mean. If you monitoring should be used to calibrate models to prognose how the damage will evolve, and then you use those models to say, okay, now my performance parameter reached the threshold, and now I perform maintenance. Exactly, this is exactly how I think we should.
Maybe that being said, some of the demonstrations here are readily indicators of remaining useful life. So the calculation of fatigue accumulation for a bridge, or damage equivalent loads as we do with filtering on wind turbines, is a direct measure of remaining useful life. So maybe one should showcase the fact that there is already a framework for forecasting, possibly even only on the basis of data, sometimes not without even the need for a detailed updating of a finite element model, which I would admit could be non-trivial for engineers, let's say, to do.
No, but I was just thinking to models, not necessarily a finite element model. Just, but I mean, my point is that we should stress this rather than damage detection, because damage detection poses a question. And now, what do I do with this information?
And added to what you say, in the exchange we had with the railway administrators, it seems that also false positives is a big problem for them. So some of the administrators that already have adopted monitoring are struggling to understand what to do with multiple false positive alarms that create need for visual inspectors to go over thousands of data within a week, for example. So that's also an issue where uncertainty quantification actually could play a role. Maybe just to ask Costas and Geert, a recurring issue here is how you tune these filters that you have shown. And for example, in the optimal sensor placement example that Costas showed, I assume that for the AKF performance, a critical factor was the tuning of the AKF, let's say.
Yeah, but we tune it for one condition using L curves. Okay.
Yes. Yeah.
Because here we run it for one sensor, two sensors, three sensors. So we just tune it for one condition, I think. I don't know the details.
And then
because
this is what I would ask. So it didn't require too much of a manual study, but then I was wondering
no,
if in fact...
We didn't retune, I think. We just tuned it for something and then we used it. But I'm not sure. I cannot answer you this
that would
thing.
be,
I haven't done it. Tulay has done it.
That would be ideal. But I was wondering, for the case where it's needed indeed to update, could this be an aspect of the hierarchical framework? So, for example, in the framework by Konstantinos that you might have seen in the previous week, they said it was sort of you can actually have a hierarchical framework using filters, but converting it in a model selection type of problem. And I wonder if the same could be done with a noise covariance selection type of
could be done, but you know, I'm not sure about the details. Could be done. Yeah.
If I can add to this,
Tatis has done. Yeah.
So for the examples that I've shown, the tuning effort was actually in the tuning of the models. So we've done a lot of effort to calibrate the models to make them as accurate as possible by also using measured natural frequencies and model damping ratios. And then in the filters, it was only the measurement noise that was accounted for. So in this way, so except for the part which involved parameter estimation, because there you
actually,
need indeed to choose the covariance.
I sort of was forced to ask because, you know, all of us know that this question pops up again and again.
Yeah.
But I agree with you that at the end of the day, for many purposes, I don't find these filters so sensitive. I think that if you have an initiating assumption that works, then you can leave it on that order of calibration, in fact. Yeah.
I have a question for Costas. Regarding the optimal location of sensors, did you find differences between, I mean, did you try situations in which the optimal location for parameter estimation, response prediction, and damage detection could be more or less the same, or there could be an optimal location that covers all
the optimal location for parameter estimation or the optimal location for response predictions are different, but you can always devise a measure that considers both. Okay, this utility or this the information gain, okay, it's built from whatever you want. You want to optimize for parameter estimation, you build a utility. For response prediction, you build a utility. You want to, and you aggregate. You want to optimize the sensor so that you search for damage in different locations. You know that the damage will happen in one location, but your sensor network should be able to you know, cover all possible sensor damage locations. Okay, you can build all that in your utility.
So you can build.
So aggregating, you know, getting an average kind of information gain, and do it like this. That's what we do actually. So
you aggregate all these utilities together.
Yes, you aggregate. Okay. Yeah. So you have your information gain from one case, information gain for the other case. You can weight how much you can weight this kind of information gain for different cases. It's like you set up a probability distribution to weight this, and you can build an overall utility.
And this information gain that you mentioned, that I understood is this DL divergence. Is it different from the value of information? It leads to
it's different. The value of information take also other issues into account, but the KL divergence or the information entropy or the mutual information, all these measures end up with the same thing.
Okay, but the value of information.
But the value of information is more than that.
Okay.
Yes, because it accounts also for. It accounts also for the consequences of different types.
Consequences,
different type of errors have different consequences. So depending on what type of error you make.
Okay, so that is different.
But You know, this what I have presented, and Geert has presented in the past, or we have collaborated on this. You can see that you don't need 100 sensors. You might need 3, 4, 5, 6 sensors. After that, you don't get any information. So you have to know this.
Yeah.
This is very important before you move to the value of information or so on.
But no, my curiosity was also if you get the same results or not with the value of information or
no,
different
because
results.
there are different kind of measures and they take into account different things.
Yeah. But probably if you use the value of information to optimize your sensor placement, which you can also do, probably you get some similar results, quite similar results than if you use KL divergence or other, as you say, entropy measures. So that, because typically, if it's for this specific problem, I mean, the valid information is probably more useful in answering the question: do you need a monitoring system at all? So it's it's more fundamental questions. Does it actually make sense to put a monitoring system in the first place, or should you rather just build a new bridge? Or so that's. I have also. Sorry.
No, go ahead, Daniel.
Okay, you go first. I will ask my question at the end.
Okay, yeah, I have a question for Professor Papadimitriou, but I think both are able to answer this because I think you've done work together in this. So you showed the two different frameworks, the classical framework and the hierarchical framework, and you showed also on a slide how this relates to the predictions and that. So my question is, both frameworks, they are based on the likelihood function, and then you make some assumption for the error. And then you can also add this error as an extra estimation parameter and estimate it on top of the parameter estimation in both frameworks. And I would imagine that the result that you get for this estimation error is quite different between the two different frameworks. And then if you use this error that you learned, then you kind of have to use this error that you learned in the predictions, right? So I was wondering, if you learn different errors between the two different frameworks, and then in both cases you use this error that you learn in making predictions, how does this relate in the end to?
I showed you an example with these modal frequencies that I learned different prediction errors from the two different frameworks. In the hierarchical, all my uncertainty most of the uncertainty went into the modal parameters. In the classical, it went to the prediction error. I show you the uncertainties that I predicted for the modal frequencies, which were of the same level. The uncertainty was similar, but one was correlated along directions in the modal frequency space, the other was not. And when I was trying to make predictions of like, probability of failure or maximum drift, you will get in completely different predictions due to the fact that the predictions errors were different.
Okay.
One didn't have prediction error. The other, the classical, all the uncertainty went there.
Maybe a question, since parameter estimation was mentioned several times, and then also Geert mentioned the aspect of observability, and I think Manolis might be in the audience. I wonder if you could give us, of course, there is the formal definition of observability, and I think that the framework as developed now nicely situates this, but you also mentioned the aspect of practical observability, and I was wondering if there's a way to formalize this somehow.
Yeah, that's a good question. I do not immediately know to answer, so I will ask Manolis tomorrow. No, but yeah, it is an issue because, like in the example of the input estimation that I showed, I mean, even if the input is theoretically observable, then the estimation uncertainty that you end up may be prohibitive. So it is something to address.
Yes, but probably requires less analytical, likely more numerical, I suppose.
Yes.
Or experimental based somehow framework. Yeah.
I read that Manol is right, that he's listening to us. We can also ask him to comment on this directly, maybe.
Yes,
Yeah, can we invite him?
I think Antonis
Yeah,
might be
yeah.
able
Also,
to give
Yes.
access. Yeah.
Yes.
Antonis has the power to do it.
I did it now. 1 second. One.
Yes.
Okay. Yes.
Yeah.
That's not the lab, Manol. It's
Lying.
I'm actually situated 2 floors below Geert's office right now. So I think the question was about
practical observability.
About the combination of theoretical and practical observability.
Not the combination, the formalization of practical observability, which can be a problem, even if theoretical observability is.
I think this is related to what Geert and what Costas were presenting. The uncertainty quantification that Costas, for example, was presenting is very much related to a framework of practical identifiability. So to develop a robust framework of practical identifiability for input estimation as well, I think the key thing is that there is a robust algorithm that calculates the uncertainty of the parameters, the states, and the inputs.
Yeah, I think this is more of why we probably need to do it on the basis of measurements also, right? So we have a feel for what the noise is and what.
Yeah.
Absolutely. What I think is very useful where theoretical observability and identifiability come in is that there are some cases that we are also investigating right now in a project with Geert, which we find surprisingly that they are theoretically unobservable. And that, for example, what happens is that even I might be spending 2 or 3 days trying to identify them, and 3 days later I say, well, let's check the theoretical observability, and you realize that it's not observable. And the algorithm has been struggling to find something that is impossible. And it's actually very difficult to see that from the results, because you would typically think that the algorithm is uncalibrated, the sensor noise is wrong, the model noise is wrong, or something like that is wrong.
What are such cases actually that could be interesting that violate theoretical observability in? So what kind of?
Well,
maybe give an example.
if you try a shear building, when we measure the inputs, I think that intuitively we would probably guess which combinations lead to theoretical observability. But if you have unmeasured inputs, there are lots of situations that result into unobservability, which are not obvious. There is an example, I'm going to give it away, because that we were trying, where we had a 5-story building, and if the parameters of that building are different between different floors, the system was observable. But if the parameters of all the floors were equal to each other, which is kind of a standard assumption that we would use in identifying a model, the system was becoming theoretically unobservable. And I've never seen such a case in situations with measured inputs. I don't think that's possible in situations with measured inputs. And it occurs from the properties of theoretical observability of unmeasured inputs. And in situations like that, you would typically blame your algorithm or your data. And it's just that thing is impossible to identify simply because all the floors have equal stiffnesses to each other.
Thank you for the input. Actually, that's maybe a nice aspect of uncertainty quantification and something that the hierarchical framework could be used with, I suppose. I think we might be exceeding our time, so I don't know, Daniel, if we
I had one more question, but I think what we'll do is we'll give the two
maybe
speakers
we can
opportunity to give a final statement, and then I will ask my questions privately afterwards. That is fine. So we will just, before we end the recording, we normally let
the speakers give
give a final message to, or maybe a hope or a vision.
Yes.
To the audience. Who wants to?
That's a difficult one, Daniel. What exactly do you expect?
Words of wisdom, yes.
We have a lot of
Wisdom.
We have a lot of young
I have to ask for my noise.
speakers, and
Well, I think I find this issue of modeling errors, model discrepancies, modeling uncertainties. I find this a highly interesting challenge, and I'm very much looking into forward to further developments in this respect. I think it's a really interesting direction of further research.
Mm-hmm.
Yeah, from my side, I would like to say that there are techniques that have been developed, like kind of strain stress estimation using output-only vibration measurements that with a little push, they can reach the companies and be able to use them for fatigue damage accumulation and fatigue prognosis that Maria Pina has already referred to. And I think we are ready to do this. It's just, we have to communicate with these guys.
On that note of hope, maybe it's a good point to officially thank you, and also thank you for concluding our series, actually, and the audience for actually being here to join us. Daniel, I think we have received requests to repeat it, so maybe we will consider it eventually as well.